In this video, we'll look at another part of the fundamental theorem of calculus. Before we discuss the fundamental theorem of calculus, part 2, first we're going to discuss the idea of accumulation function, which is a new type of a function. I'll explain what accumulation functions are and why they're so important and useful in calculus. Here's an example of an accumulation function. It looks like a definite integral, except there are two variables. T is used as an input to f, and x is used as input to a and the upper bound of integration. You might be wondering, what is this and why is it useful? To start to think about this, let's look at the behavior of an interesting creature. The Crested Platypus is a creature that lives in and around the deep lakes of New York State. When it is ready to mate, the male Crested Platypus enacts an interesting dance. As it dances, the platypus rapidly waves its crest, which causes it to levitate off the ground. To understand this levitation a little better, let's make a graph of its velocity in meters per second as a function of time measured in seconds. We'll graph the velocity as we watch it. Now that we have the information about the velocity of the platypus, let's use it to get some information about how far the platypus levitates around above the ground. Let's first set the value of x equal to 2, as shown by the red section of the graph. Thus, we'll be looking at the first 2 seconds of the platypus motion. Now we want to compute the platypus amount of change of distance from its starting position over these first 2 seconds. To do this, we'll look at the velocity of each moment in time multiplied by these values by small amount of change in time. Then add these amounts of starting at time 0 up to our value x, which is 2. And when we let the value of t increase from 0 to 2, then the value of this definite integral is represented by the area between t-axis and the graph of the velocity function between t equals 0 and t equals 2. Next, let's increase the value of x from 2 to 4. This will change the upper bound of the definite integral to 4 because we'll now be considering the first 4 seconds of the platypus's motion. And when we let the value of t increase from 2 to 4, then the value of this definite integral is represented by the area between the t-axis and the graph of the velocity function between t equals 0 and t equals 4. Next, let's increase the value of x from 4 to 6. This would change the upper bound of the definite integral to 6 because we'll be now considering the first 6 seconds of the platypus motion. And when we let the value of t increase from 4 to 6, then the value of this definite integral is represented by the area between t-axis and the graph of the velocity function. Now we've computed the total accumulated distance at these different positions in time, at 2, 4, and 6 seconds after the platypus started levitating. But we could have computed this for any point in time, which we show by writing an x in the upper bound of the definite integral. And when we can think of this as a new type of function, the total accumulating distance function. Now, one thing that might look a little strange is that there are two variables, t and x. Both t and x are time variables. However, they serve different purposes. The x variable tells us that we're accumulating distance from 0 to x. And the t variable is used to as a product of vt times dt to compute the distance. Now we can think about what the function d of x looks like. Here's a graph of v of t in red. And we'll graph d of x in purple as both the accumulating area and a curve. In this graph, we can see that we're accumulating distance quickly at first, and then slowly, and then quickly again at the end. The y value of the purple curve at each value of x is the amount of distance will be accumulated between time 0 and time x. And this is also the area between the t-axis and the red curve between 0 and x. In general, anytime you have a definite integral where the variable is on the upper bound of the integration, this is called an accumulation function because it tells you how much of a quantity you accumulate between the starting point and the value of the variable. Now that we looked at the idea of a new function called accumulation function, I'll show you how to use accumulation functions to construct antiderivatives. First, let's remind ourselves of what an antiderivative is. If you have a function, little f, then big F is an antiderivative of little f if the derivative of big F is equal to little f. For example, if little f of x is cubed, then big F of x will be 1/4 x to the 4th plus some constant c, because the derivative of 1/4 x to the 4th plus c is x cubed. But what if you had a function like e to the negative x squared? You can't use the power rule or rules for exponential functions. Unfortunately, none of our basic derivative rules work. The formal way to say this is that little f of x does not have an elementary antiderivative. It turns out that you can use actually the accumulation functions to construct the antiderivatives. Let's look at an example and think about it in terms of velocity and distance. Let's start with a graph. Here's a set of axes. We'll think of the function v of t equals to e to the negative t squared as it describing the velocity of a car. We can draw a graph of this velocity function in red. Next, let's think about an accumulation function. Here, d of x tells us the amount of distance the car accumulates between the time -3 and time x. We want to know about the rate of change of this accumulation function. For example, if we imagine the distance accumulating, we can ask how quickly the distance accumulating when x equals -1. It is difficult to determine this because the rate seems to be constantly changing. To make things a little easier to think about, let's imagine a Riemann sum approximation of this total accumulated distance. Let's think about what this Riemann sum is telling us. If we look at these bars, we know that it has width that corresponds to the amount of change in time, in this case 1 second. Also, it has a height that corresponds to the velocity of the car. Now, the reason this bar has a horizontal top is because we're assuming the velocity is constant throughout the entire 1 second interval. And when we multiply constant velocity by the amount of change in time, we'll get the amount of change in distance, which is represented by this area of the bar. Let's think about the rate of change of distance with respect to time just for the interval between -1 and 0 seconds. Since we're assuming the velocity is constant, then the rate of change of distance is the ratio of the amount of change in distance and the amount of change in time. When we do this, we're dividing the area of the bar by its width, which gives us its height, which is representing the velocity of the car. Let's take a closer look at what this means. If we start at -1 seconds and imagine the value of x increasing, how quickly are we accumulating the area? For this bar, its height tells us how quickly we're accumulating the area as we increase x. So the value v of t tells us the rate of change of distance as we increase x. Similarly, if we keep increasing the value of x, now we're accumulating area at a much faster rate. Once again, the value of v of t tells us the rate of change of distance as we increase x. And we could imagine doing this using a Riemann sum that has much shorter intervals. In particular, for each value of x, the rate at which we would accumulate the area would be given by the height of the graph. That is the rate of change of distance would be given by the value of the velocity function. And if we shrank our time intervals enough, then the rate of change of distance with respect to time will be the same as the instantaneous velocity. Thus, the derivative of our integral, d prime of x, is equal to the velocity function evaluated at x. Let's think about what a graph of accumulation function would look like. For each value of x, the value of accumulation function, the graph in black, tells us the amount of distance we've accumulated between time 0 and time x. We can see that value of the velocity function tells us the slope of the accumulation function. And now, since the derivative of the accumulation function is equal to e to the negative x squared, this means that d of x, the accumulation function, is an antiderivative of e to the negative x squared. So in general, if you have an accumulated function of a of x for a function f of x, then a of x is an antiderivative of f of x. Another way to express this is that derivative of a with respect to x equal to f of x is equal to f of x. And this is one part, so the another part of the fundamental theorem of calculus.